Hi Karthik, hi Tulsi. Okay, shall we start our presentation?
Yep, ready.
Okay. Hello everyone, welcome to our feature engineering final project presentation. I am Akila and today along with Karthik and Tulsi we'll demonstrate our comprehensive audiovisual feature engineering and classification system. Our project tackles three major objectives. First, extracting rich multi-scale features from audio and video, and the second is creating novel cross-model synchronization metrics that capture temporal alignment between sound and motion, and the third one is building the interpretable machine learning models with extensive visualizations. By the end of this demo, you'll see how we achieve the accuracy of the classification on urban sound 8K while pioneering new techniques in multimodal feature fusion. So, the first section is the foundational implementation before diving into our structural analysis. So, let me explain the core implementation that powers everything in the project. So we basically built three foundational engines. First, our audio processing engine was to extract audio features, which standardizes to 16 kilohertz and computes over 2,471 features per sample, including the MFCCs with delta and also delta delta derivatives. And we compute nine statistical summaries, which are like mean, standard deviation, minimum, maximum, median, 10th, and 90th percentiles, skewness, and cortices. This transforms variable length audio into fixed length vectors, which are suitable for machine learning. And secondly, our video feature engine uses a pre-trained ResNet 18 to extract the 512 dimensionals embeddings from evenly sampled frames, which combines this with optical flow for motion analysis and computes scene change metrics. So this produced around 1040 video features per clip. And the third most innovative is our cross model synchronization function, which computes around six metrics. So they are like Pearson and Spearman correlation between audio energy and video motion. And the other one is like maximum cross correlation, allowing for time lags, mutual information for nonlinear dependencies, synchronization mean square error, and peak coincidence ratios. All these three engines include like the robust validation to handle corrupted files. And coming to the setup and data loading. So now let's walk through the section 0 and section 1. So we begin like by implementing the necessary libraries like the NumPy and Pandas for data manipulation, Librosa for audio processing, OpenCV and PyTorch for video, and Scikit-learn for machine learning. So we mounted the Google Drive for persistent storage and created an organized directory structure with separate folders for the raw data. And we are working on like two data sets, which are like Urban Sound 8K and the VGG Sound, which are having like 4,612 samples, and we have like 25 video samples from the VGG sound for the cross model analysis. The metadata exploration immediately, which reveals the important insights such as urban sound 8K, we see relatively balanced classes with 400 to 800 samples each. However, the VGG sound sample shows extreme sparsity with one only sample per class. So, coming to the utility functions, which is the most critical summarize vector, which converts the variable length sequence into fixed length statistical descriptors. So we also implement validate audio file, which checks for silent audio and also extremely short clips and invalid values. So coming to the section 3, audio feature extraction and insights. The section 3 is like the comprehensive audio processing block. So using the libraries Librosa, we extracted like 2,471 per samples. So let me break down this first. Uh, So it included like 1080 MFCC based features from 40 coefficients plus their first and second derivatives. So each summarized with different nine statistics. So 1152 were Mel spectrogram features from 128 frequency bands, the roll off and flatness. So the other were like 162 harmonic temporal features, including RMS energy, zero crossing rate, onset strength, the tempogram, tempo, and harmonic percussive ratios. So our correlation heat maps reveal strong blocks of highly correlated features. So which especially within the MFCC families, which were adjacent coefficients naturally, and also they represent neighboring frequency bands. So from here, my friend Tulsi will explain the section 4 about the video feature and processing. Thank you.
Thank you, Akila. I am Tulsi Sai Jalpati and I will cover video pre-processing, our key innovation, cross-model features. In section 4, we use ResNet 18, a pre-trained CNN to extract semantic visual features. We sample 10 evenly spaced frames per video and extract 5 12-dimensional embeddings from the penultimate layer. Computing mean and standard deviation across frames gives us 1024 CNN features. We then add dense optical flow using Fennebrake algorithm to measure motion magnitude, scene change detection, and color statistics. This produces 1040 video features per clip with zero extraction failures. Our visualization reveal important patterns. Motion features show wide variation, calm ocean waves around zero point 0.5, the dynamic moments exceeding 5.0. Correlation heat maps show optical flow features cluster tightly due to their shared origin, while CNN embeddings show independence, reflecting hierarchical specialization. This validates our video pipeline produces meaningful interpretable features. And here we go to the section 5, cross model innovation. Now, in the section 5, our most innovative contribution, cross-modal synchronization features. Traditional approaches treat audio and video independently, missing the temporal relation between sound and motion. When a door slams, there is both loud sound and visual impact. Our features explicitly capture this alignment. We extract audio energy via RMS and onset strength and video motion via optical flow. After interpolating to common temporal resolution, we compute 6 metrics. First, Pearson correlation measures linear relationships. Second, Spearman correlation captures monotonic dependencies. Third, maximum cross correlation finds strongest alignment, allowing time lags. Fourth, mutual information quantifies nonlinear dependencies. Fifth, synchronization MSE measures alignment quality. Sixth, peak coincidence counts matching audiovisual events with narrow time windows. Cross model results. Our visualization suite shows histograms across 19 VGG sound sample. Pearson correlation peak at the 0.3 to 0.5, showing moderate synchronization. Spearpen values are slightly higher, confirming monotonic relationships. Cross relation maxima above 10 indicate strong event alignment. Mutual information ranges 0.5 to 1.5 bits, confirming nonlinear coupling. Peak coincidence ratios from 0.2 to 0.8, with many above 0.5, meaning most audio events have matching visual events. This validates our cross-model engineering captures real audio-visual relationships, features single modalities cannot access. Now we go to the section 6, pipeline execution. Pipeline execution executes our complete pipeline. For urban sound 8K, we process folds separately. Fold 1 extracts 863 of 873 files. Fold 2 gets 879 of 888 and so on. Small failures are corrupted files caught by validation. Each successful sample yields 2471 audio features plus metadata we save as Parquet files, then concentrate into a master dataset 4579 samples by 2475 columns. For VGG sound 19 videos, we extract all three feature types 2471 audio, 1040 video, and 6 cross model metrics totaling 3517 features per sample. Logs confirm zero failures, consistent dimensionality, successful Parquet saves. Total time 12 minutes for urban sound 8K, 2 minutes for VGG sound. This verified pipeline forms our foundation. Feature engineering complete, over 3,500 features ready for analysis. Now I'll pass to Karthik for machine learning results and visualizations.
Thank you, Tulsi. And so I'll continue from here. So coming to the section 7 of the of our implementation, that is the machine learning preparation. So here I'll be covering our machine learning pipeline, visualizations, and results. Also, the section 7 prepares data for analysis. That because that's the only part left after all the data is prepared and everything. We have a huge number of samples now, around 3,500 plus. So we separate features from metadata, then apply simple imputer. Here you can see that we applied a simple imputer, which means with mean strategy. This is mainly to handle missing values and critical step often overlooked. And the standard scaler normalizes features, as we all know, to zero mean and unit variance, which is very essential for SVM and PCA. For VGG sound, we only one sample per class prevents stratified splitting, which perfectly aligns with our feature engineering focus. And for urban sound 8 case balanced classes, we perform stratified 8 to 20 split and then apply PCA, requesting around 95% variance retention. This reduces the data from 2,471 dimensions to just uh, 407 components. That is well, like 6:1 compression. This is not this also preserves the all the information, not there's no loss in that. This confirms that more information lies in the smaller manifold, but computationally efficient and statistically favorable. This is like because there's no loss, or we are preserving the all the information. We have done the PCR on that, even though there's no loss. And coming to the section 8, that is the visualization, that is around like 10 analysis visualization and their analysis. Uh, so then the coming to the we'll directly go step on to the visualizations, as this code is everything similar to us. Every visualization is shown using this code and the stuff. So we'll directly step into the outputs. So the first visualization shows distribution across classes like MFCC. Zero varies dramatically. Air conditioners at minus 400, dog box at minus 100. Musically, music near zero. So yeah, the tempo separates rhythmic sound at 120 to 140 BPM from rhythmic to 60 BPM, explaining the discriminative power. And the visualization 2, it's a correlation heat map showing strong blocks MFCC 0, 5 correlate above zero point 0.8 as adjacent bands carry similar information. Blue regions show negative correlations like harmonic versus persuasive ratios. Relation 3, that is PCA analysis, has three panels, like left shows 407 components for 95% variance, but 50 explains 75%. Middle shows 2D projection where the dark bulk and the air conditioner cluster tightly, while children playing and street music overlap. Right shows PC1 on MFCCs, PC2 on special features. So coming to the visualization for that, TSNE shows distinct islands of dark bark, air conditioner, and gunshot, confirming high separability. Coming to the street music and children playing overlap, validating similarity. The visualization 5 gives us like the feature importance about the top 30 dominated by MFCC statistics. With the delta and delta ranking high, the cumulative plot shows 90% of the power from 800 of 2,471 features. Yeah, these were the visualizations for those, the top 30 features. And coming to the visualization 6, the breaks down by category. That's MFCCs account for 20% import for 40% importance, despite 30% for features most important, information dense. And mail spectrograms contribute 25%. So yeah, and spectral contribution around 15%. So visualization, so we'll move on to the next visualization and discuss about the analysis later. Visualization 7 confirms class balance with around 450 to 500 samples. Each and proper train and test stratification is done here, and visualization 8 shows 10 features that had missing data now imputed. Temporal features have high variance. And coming to the next visualization, there's a visualization 9 is a dendrogram, which is showing like clear grouping MFCs. Um, MFC is clustered together, chroma separately, and validating distinct information captures. And as continued by the dendrogram, we have visualization 10, that is learning curves that shows CV score reaching 85% and M1 macro with small training validation gap, indicating good generalization. Rising curve suggests more data could reach 90%. So, yeah, this is our visualization and analysis that we were able to make up from our data and through machine learning and some PCA. So this is a pretty good analysis we were able to make. And in the section 9 models and evaluation, the section 9 5 models, logistic regression and raw features, 91.8% accuracy, 92%, that's F1 impressively high for linear models. The logistic regression on PCA, that's 90% confirming PCA preserved information. The random forest on raw data, that is 90.4%. The random forest on PCA is 89.8, which is the winner. The winner is SVM with RBF kernel on PCA features, that's giving around 95.4% accuracy and 95.5% F1. The RBF kernel finds complex decisions boundaries. Through this, we can understand that is a winner. And yeah, these were all the like the model training and the visual. You mean we got the accuracies, F1 scores that were calculated. And coming to the section 10, these are the other visualizations for um, evaluation. We can say the visualization 11 compares models SVM PCA dominates here, and visualization 12 that is the confusion matrix shows main errors children playing misclassified as street music. 8% both have complex spectral patterns. Dog bark achieves 98% precision from distinctive transients. And visualization 13 shows per class performance. That's 8 conditional, 97% across metrics due to unique tonal drone, gunshot, 96% precision, and so on. The same, you can also consider the street music lowest at 89% F1 due to diversity. And coming to the next section, that is a section 11, there's a cross model analysis. This section in the section 11, it's basically because for the sound cross model features with visualization. And so here I have made visualizations basing on the histograms. Person correlation peaks at 0.3 to 0.5, and showing moderate synchronization summary 0.7 in musical performance, and cross relation maximum range 5 to 20, most around 10. Mutual information 0.5 to 1.5 bits confirms modalities share meaningful information. The synchronization MSC 0.5 to zero point 0.1 shows reasonable alignment. Peak coincidence 0 to 0.8. Many are above zero point 0.5 among all the visualizations, meaning most audio events match visual events. These prove our class model features quantify audio-visual relationships, enabling future fusion that could exceed 95%, which we have achieved in this implementation. So these are all the visualizations and everything got saved in our data base. And coming to the conclusions, the key achievements are first, production-ready pipeline processing 4,579 audio and 19 multimodal samples is like appreciable concept where generating 2,517 features per multimodal sample. And secondly, it's a 14 relation revealed MFCC dominance at 40%, 6 to 1 PCA comparison. And the third thing is 95% accuracy around with SVM approaching human level performance. And the fourth thing I can say is the cross-model feature successfully synchronizing using correlation and coincidence. So the final but not least, it's a fifth. It's a learning curves. You can see the 97 to 98% suggest they suggest it's possible with full data set. And this is what we can conclude in like 5 points. And according to our according to this work, we can say there's some future work possible, and that is like, yeah. So I can say we can extend it to some other CNN models, LSTMs, and also some other, we can use noise monitoring systems, security for anomaly detections, and many other engineering demonstrations. So yeah, this is what like CNN or LSTM with according to the real-time optimization, multimodal fusion architectures, transfer learning from audio set or attention mechanisms can be included. Also the cross data set evaluations like SK ESC50 and FHD 50K are some of the uh, engineering techniques. And production deployment with the REST API. This can be done on any with any APIs, not only REST APIs. And yeah, this is what I wanna explain on the on a total my pipeline implementation. Thank you for watching, and comprehensive feature engineering this is our feature engineering demonstration in which we have majorly focused on feature engineering, not on the like machine learning is also a good part we have done, but it's a majorly feature engineering focused project. Yeah, thank you. Have a good day. Yeah.
Yeah, thank you, Karthik. So I guess we can stop the recording from here.
Yeah, I'm about to stop the share, and thank you everyone. Thank you,
Thank
Tulsi.
you, Akhil and Karthik.
Thank you, Akila.
Thank you.